Yes, good afternoon, guys. This is one more problem. In a previous video, we did acceleration for different mechanism, and here it is another mechanism, and this is a 4-bar mechanism which has a PQ. There is a length of the PQ and QR, RS, PS, and angular velocity of PQ. Angular velocity of PQ, it is rotating in a clockwise direction. So, how they are framing a question, right? So, this is how they are giving the angular PQ link. The PQ link is rotating with some angular velocity that is 10 radian per second and with an angle 60 degrees, right? So, PS is a fixed link. They are given that PS is a fixed link and QR is as same as above the parallel to this, right? And these are the given data and how to get a space diagram, right? So, space diagram, as I told you that here in the previous diagram, that we have to take a scale. We have to take a scale of this and we have to convert into centimeters, whether it is a 1:2 or you can take whatever. Okay, so if you see that this is a 0.625 meters is there. Okay, so you can consider 0.625 meter is, it may be a 6 centimeters. So like that we have to take, we have to consider the scale, whatever it is up to you. So after getting we have to take a same scale, same length, centimeters in centimeters, we have to frame a space diagram. Then after they are asking to find the angular acceleration, angular velocity of these different links. As a PQ that we will find and QR and RS. So here if you see that velocity of Q with respect to P, that is the one thing, and velocity of R with respect to Q, velocity of R with respect to S. If you see, observe here, velocity of R with respect to Q is one value, then the velocity of R with respect to S, this is a fixed one. S is a fixed one. So, we have to find these terms and the formula for this is omega QP is a RQ omega RQ. So, like this we have to get the values. See, and this is the value which is given, that is QP that we have, PQ that we already got, that is 0.0625 meters, and omega, angular velocity is rotating in clockwise direction. So here it is a 10 radian per second. So we get 0.625 meter per second. So this is the value, and these are the values we don't know, right? So this is the value which we will get direct from the diagram, velocity diagram. Let me draw the velocity diagram. So while we are drawing this velocity diagram, that we have to consider that the velocities are acting perpendicular to those particular links, right? So the known term is this velocity of Q with respect to P, that is 0.625. This is the magnitude. What is the direction of this, right? So direction of velocity of Q with respect to P is always perpendicular to that particular link. So this is, if you see that, that is a perpendicularity to that particular link. So that is the direction, and here length, how much that we have to, that is up to us, that I can consider this is a 4 centimeter or 5 centimeter or 6 centimeters. This is the velocity that we are representing in centimeters. Okay, actually it is a meter per second, we are converting into centimeters. So yeah, PQ is a fixed link. So whenever we have a fixed link that we consider as a point, that is PS is a fixed link. So if we consider this is a perpendicular to this PQ, right? So this is velocity of Q with respect to P. So in this direction, if you see that we have to take in this direction the same. So this is velocity of Q with respect to P. So how much? 4 centimeter, that we have to take that. The next, consider velocity of r with respect to q. This is also perpendicular, right? So how we have to take a perpendicularity, right? So this is a p and this is a q, right? And the next, the same as a perpendicular that we have to take it here, a velocity of r with respect to q, right? Again, velocity of r with respect to s, right? So if you see that here we have getting a perpendicularity, right? So perpendicular to this particular link we have to take. So first I have to draw here velocity of r with respect to s. First I will take, because it is a fixed link, and this is like this. I will get a perpendicularity of velocity of r with respect to s. So this is a perpendicular. So I am taking it here. That is, this is the point s, right? So that is, we don't know the value, exact value of velocity of r with respect to s. Is simply we call it as the velocity of r. We'll call it as velocity of r. Then after we have to take a perpendicularity of this, and here it is perpendicular. I am taking a perpendicular for this link, for this QR link. So these two are perpendicular, right? So I am taking it here. So this is the value of r, okay? And the direction it comes, it is like this, velocity of r with respect to q, okay? So that is the value, and we can find it here, the centimeters. We can find it in a centimeters, and here also we can find it is in centimeters. So we can substitute it here. We can substitute it here directly. That is velocity of r with respect to q and velocity of r with respect to s. So these two we can substitute here. We can convert into, this is a centimeters. It may be a 2 centimeter or 3 centimeters. Okay, so we have to convert into meter per second. We will get the values at here. So here main thing that we have to concentrate is how to find out the magnitude and direction for a velocity to find out the velocities. And the next one, coming to the acceleration, right? So for acceleration, that we have to find the two components. In a previous video that I already explained you, the two components that we have, a radial component and one is a tangential component. So let me find out this radial component and tangential components. Okay. So for the first one, the radial component of PQ, right? QP, isn't it? So as I told you that in a previous video, here you see the radial component of Q and P, the radial component, tangential component of QP with respect to P. Here it is, the tangential component is not exist because the crank PQ is rotating with a constant velocity, so we are not considering this. And the next, radial component of R with respect to Q and the tangential component of R with respect to Q. So these are, so yeah, next to radial component R with respect to S, tangential component of R with respect to S. So if you write like this, what are the links that we have? Okay, what are the components for that? So if you write like this, so that we will get a clarity how to make a acceleration diagram. So you see it here, velocity of P with respect to V square by QP. This is the formula for radial component. So this is the value which are already got, right? So that we can substitute it here and we will get the value in meter per second square. So coming to the here also same, these are the values that we will get from the previous velocity diagram. So these are the values we can get directly from here, right? In a centimeters, we can convert into meter per second. So those are the values we got. Okay, so we can substitute directly here, we will get the values meter per second square. So this is the value which comes from the diagram, right? So the next, the same, this is also velocity of r with respect to s whole square by and rs. This is the length of the link. So this is we can get from the diagram. So these are the terms that we have to get from the formula and from the diagram. So coming to the diagram, coming to the acceleration diagram. So yeah, same that we have a 4 links. One is PS, PQ, RS, QR. So PS is a always fixed one. So I have to consider fixed one. That is a PS. That is a 1 point. PS is a 1 point. So coming to here, the PQ, right? That is a PQ. Here it is. First, suppose that I got a value of it. Here it is at most 6.625, maybe the value that we will get it here. So I have to take 6.625 meter per second square is 6 centimeters or 5 centimeters, whatever that we have to consider. So that is the value that we have to take it here. And the direction comes, as I told you, that radial component is parallel to the link. The direction is parallel to the link. So how this is, PQ is like this. So the same I am taking it here, PQ. So this is a radial component of Q with respect to P. Q with respect to P. So that is 6 centimeters. Just I have to take, we have to take a 6 centimeters. Then again come to the radial component of R with respect to Q. So we will get a value something else at here. It may be a 3.34 meter per second square, right? So we have to convert this 3.34 meter per second square into how many centimeters, right? So radial component is parallel to that QR. So again this is a QR. It may be get a 1 centimeter, right? So I have to take it here. It is right. A radial component R Q. And the next coming to the tangential component. Here it is a tangential component. We don't know the value, we know the direction. The direction is perpendicular to this QR. So perpendicular. So I am taking here it is perpendicular. So ATRQ. That is acceleration tangential component R with respect to Q. Isn't it? So again come to the R with respect to S. R with respect to S. So coming here, radial component, we already get the value from the data. We already got here RS, velocity of RS and RS. So we will get some value at here. So we have to convert again into centimeters. See here we have to observe that we have to every time we have to convert it. Whatever the known value of radial component, we have to convert into centimeters. So it may be get 2 centimeters, and this is a radial component of R with respect to S, isn't it? So that is why I am taking here like this, because RS is like this. So I have to take parallel. So radial component is parallel. Next, perpendicular we have to take. Tangential component is perpendicular. So perpendicular is like this. So I am taking it here. This is ATRS. So this is the value, this is the point which we got, that is R. Right? So while we are joining this, if you can observe here, one is radial component of R with respect to Q, tangential component of R with respect to Q, radial component of R with respect to S, tangential component of R with respect to S, right? So I have to make final acceleration of R with respect to Q. So this is the R, point R, that I am joining this, here it is. This is A with RQ. So that is a resultant. So when you have a two component, that we have to make a resultant. So this is the resultant acceleration of r with respect to q. As the same, this is the resultant see this. This is acceleration radial component of r with respect to s, tangential component of r with respect to s. So these both we will get, here it is r with respect to s. This is okay. So from here that I got three triangle shape, that the triangle shape is this. If you observe, this is the triangle shape, the finally we got it. So from here we can get the tangential component centimeters, in centimeters, and here also in centimeters tangential component. Okay, so centimeters we have to convert into again meter per second square, So whatever the finding element that we have to convert from here, so you don't confuse that while we are doing an acceleration diagram. It's a very clear. We have to find first radial component, what are the radial components, and the tangential component that we have. We can find it out by using a formula for by using a previous data. So that data we are using to draw a acceleration diagram. Then after we are finding out the tangential components by taking a perpendicular to the link. So the only term that we have to remember every time is radial component is parallel to the link and perpendicular to the link is a tangential component. So these two, while we are calculating a resultant acceleration. So this is the term we got, and we are getting a tangential component by taking a centimeter. That what we got at here, we are converting into meter per second square. This is all about for a 4-bar mechanism. Thank you.